Hello everyone, my name is Mobin Shakeri and I'm a PhD candidate at the University of British Columbia, working with Professor Matthew Choptik. Today I'll be talking about importance field, physics-informed neural network for solving hyperbolic forward and inverse problems in the context of numerical relativity. So before starting to discuss the method, let's briefly talk about the overview of the problem at hand. When we talk about forward problem, we're referring to solving Einstein's field equations, more specifically solving full EFE of a binary system of black holes or neutrino stars. The inverse problem focuses on taking the observational data, such as the signals that are detected by LIGO and Virgo, and we're inferring the physical parameters of the binary system. Now, these problems are usually computationally very demanding, and our goal is to improve the efficiency of solving them using machine learning. Now, first, let's look at the standard approaches used today to solve the forward problem. In a standard numerical relativity approach, we first decompose the PDEs and the operators into a 3 plus 1 decomposition of space-time. And then we separately simulate for each specific parameter. And then we extract gravitational waves from it using there are many sophisticated approaches, but one very straightforward way to use is just to use the Newman-Penrose psi-4 scalar as to get the gravitational wave, and then we can create a gravitational wave bank from the results. The downside of this approach is that it is very time consuming and computationally expensive. Uh, Now that we have a gravitational wave bank, noted here as capital H, we can create a surrogate model from it, and there are many different methods to do so. And a basic umbrella term for it is called ROM, or reduced order modeling. Currently in LIGO Virgo project, the ROC, or the reduced order quadrature, is used, which is a method based on greedy algorithm and has a empirical interpolation implemented on the basis. Um, so currently it takes around 6 months of offline work, and calculation of the bases are done and could take around days for each online work, which means each observation takes around the order of days for its parameters to be estimated after the bases are calculated uh, from the bank. Now, this is too slow, especially for the next generation of gravitational wave observation, when we expect a higher frequency of observation and probably more complicated ones, such as neutrino star collisions. So this brings us to our motivation to explore newer faster methods, and one of those options are machine learning techniques. Um, so basically, to overcome these computational challenges, we turn to neural networks, which has strong function approximation capabilities. The universal approximation theorem tells us that any function can be approximated by enough step functions. And if we see neural networks as as an interconnected, linearly transformed activation function, step-like activation function. We can see that they can be used as an approximation of function itself uh, in the forward problem. Um, and and now there are many methods used to replace the traditional methods, such as uh, finite difference method, but probably the most famous one for solving a forward problem is PINN, or physics informed neural network. Also, for the inverse problem, we can use the network as a surrogate model, such as the Bayesian posterior distribution. And this work has been done already in models such as Dingo, and already show a significant improvement from online works of orders of days to orders of minutes. Now let's quickly overview PINN method uh, before moving on to if pin. Uh, so if you have a general Cauchy problem of this sort, with D being the differential operator, and with some appropriate initial condition, of course, to the order of k, um, and some boundary conditions, we can define a loss function like this, um, which is a normalized mean squared uh, of the PDE residuals. So each term of the summation is the PDE residual, and it is mean squared. And they are also normalized with n of I, n of b, and n of the uh, c, which is the collocation, the boundary, and the initial points. So the obvious advantage of this method compared to the traditional ones is that it does not require a grid. Therefore, we won't be having the curse of dimensionality anymore, which makes it specifically very good for higher dimensional simulations. Now, PINNs are very promising, but they struggle with hyperbolic PDEs such as Einstein's evolution equations, and it has a slow convergence still. And it also requires a very large number of collocation points, since at the end of the day, we usually end up grading the domain anyway. Now, to address these challenges, we introduce a new method called importance field physics informed neural networks. We try to define the importance field on top of other fields on space-time to accommodate these issues. The basic idea is that the importance field selectively assigns higher weights to critical regions of the domain. These importance fields act as a modifier for the loss function, and it is used as a distribution probability of the collocation point which we put inside of our domain. So instead of treating all the points equally, we define an adaptive importance field to focus on training on the most relevant regions. Therefore, this leads to better accuracy and also faster convergence and more efficient training. The level zero importance field, in defining the importance field, is the event's importance, which accounts for the position of boosted events towards each other, um, without any interaction with each other. So having that event's importance defined, now additional to that, temporal importance, which incorporates the causal structure of space-time. Uh, we introduce a causal weight W to give more importance to prior times. In this way, this works by defining W as the exponential of all the temporally previous terms of loss, as you can see here. Uh, the learning prioritizes the earlier time slices. Um, this helps to enforce causality and ensures the model learns wave propagation dynamics correctly. For example, we can see a snapshot of this W in blue here on the right panel. And you can see that on the left panel, how it is affecting the loss function. And you can see that the loss function is approximately zero at posterior times. This will force the learning to focus on the prior times before the weight eventually turn to 1 and the loss converges to the orange dash on the above here. So it it kind of lets the system learn from lower times to higher times in order, therefore it follows causality, and this causality is informed in a light cone from any event in space-time. For the boundary term, we aim to remove it altogether, since reducing objective in multi-objective learning can enhance learning significantly, so we aim to do that. We can do so by altering the network architecture actually to implement the boundary condition. So now to do so, we can use different approaches based on the specific boundary conditions we're using. So if you're using a periodic boundary condition, we can add a Fourier feature embedding of this sort to the beginning, to the order of m of sine and cosine. The higher it is, the more oscillation and more accuracy, but higher calculation, of course. For a Dirichlet boundary condition, we can use an embedding of a distant function from the boundaries, and we can set the specific value of the function at boundaries to match our given Dirichlet condition. Now, since we're dealing with a gravitational wave extraction at far boundaries, ideally infinity, it is better to use a compactified coordinate to completely remove the BC error, because if we want to cut off at a large boundary, we're still going to see some boundary condition error, but in another form, in the form of collocation error. So to completely remove that, we use a compactified coordinates. In addition to time importance, we also can define a spatial importance field like this. The spatial importance comes from the specific form of this compactification transformation. And we can always numerically change the inverse of this compactification function, to and then have a cutoff around zero and interpolate it to the zero, um, which is always a good guess. One can also guess another function for spatial importance if it generally follows the inverse of the compactification transformation. Now, the another importance field is the error importance field, and this would be the adaptive part of this method. So this the model continuously evaluates which region have higher errors as the learning goes on and epochs goes forward. And if the uh, local error at that spot is more, the basic idea is that it will generate more training points in those area. And here, by this hashtag sign, I mean the number of epochs. So this is the adaptive part, which will change as the training goes on. So in general, we can define our importance field like this. The temporal part cross the spatial part plus the error field plus some constant diluted field C. And this C can be seen as like a background um, coarse grid. The good thing about this approach is that it generalizes many of the previous approaches. For example, it is well known that PINN method is not good enough around the boundaries of the domain. And one of the famous approaches to this is to pass the network to a weight function, as you can see here, to prioritize the middle collocation points. Now, by having like an exact BC and a causal temporal field, we automatically solve this issue uh, as well because we are, in a sense, we are passing this the network through this already. And also the method incorporates causality internally, and it has a reduced training batch, which are all better points compared to PINN, and it is faster in training, and also it removed the boundary condition. So hopefully it will be better for more highly nonlinear equations. So as a result, to validate our approach, we apply the if bin to test the case of non-topological soliton, and the results are as here. You can see the results, the errors, and these are the final epochs after a training of around an hour. And the results show significant improvement in an accuracy in convergence compared to the standard pin. The error reduction is observed, and especially in higher gradient regions. And this just demonstrate the power of adaptive importance field in improving machine learning based PDE solver for specifically forward problem. There's still some work to be done to be fully implemented uh, on a full Einstein field equations, but more work is in progress. So thank you very much for the attention, and if you have any question or would you like to discuss this, please feel free to reach out to me, and that's my email. Thank you.